Welcome back, Contemporary Math. We are in Chapter 1D. We are finishing up the section on logic today. This is 1D, analyzing arguments. And so we start off this with talking about the two types of basic arguments. And so this first one, we have the premises. So I didn't study for the first test and I failed. I didn't study for the second test and I failed. I didn't study for the third test and I failed. And so the conclusion that they're going to draw there is, therefore, if I do not study for a test, I will surely fail. Okay. So if you read this, this seems like a pretty reasonable conclusion. And this is a sort of example of an inductive argument. So you see a sort of event, you see another event, you see another event, and you see this sort of, maybe you see a pattern starting to emerge, right? And so this is what's known as inductive reasoning. Deductive would be something like that cliche example I threw out at you at the beginning, right? All men are mortal, Socrates is a man, therefore Socrates is mortal. And so we want to think about this. Is this a necessary conclusion from the things that are happening here? And so if we think about this, if we don't study for a first test and you fail, you don't study for your second test, you don't study for a third, and you keep bombing them, pretty good, what do I want to say? Pretty good indication, if you know how things are working in a classroom, that if you don't fail for the next one, you're probably going to fail it, right? But is it guaranteed? It's absolutely not guaranteed, right? There's always those weird things where you don't know what the heck you're doing on the test, but somehow you just answered all the correct answers, or vice versa, right? Maybe you think you're doing well and you didn't. So there's no guarantee that you're going to do well or do bad on a test. There's lots of other factors that come into play. If we look at this other argument, we know all men are mortal, Socrates is a man. Is this a necessary conclusion from the premises that we have? And it absolutely is. There is no way to get around this. Socrates has to be mortal. If all men are mortal and Socrates is a man, he is mortal. And we will go a little bit more on how to analyze these sorts of arguments. This is a valid argument. And so this conclusion will be necessary from these two premises. And so they give us a definition of inductive versus sort of deductive. And the way that they define things, I think, is okay. But inductive, it makes a case for a general conclusion from more specific premises. So in other words, like, you have these events that are happening, right? And so you're trying to notice a pattern that might be happening. You're trying to draw some kind of general conclusion from specific instances. Deduction, on the other hand, you're saying something very general. You're saying something about all men. You're saying something about a member existing within that set of men, right? And if it's within the subset, it's also within the larger set of things being mortal. And so Socrates also has to be within the larger set. And so what we're doing is we're making these general sorts of statements about all men. And from there, we're making a very specific conclusion about Socrates, about a specific individual. And so in math, we actually use both of these a little bit, right? But this doesn't actually ever prove anything, right? This is what we talk about when we talk about proving things in math. Because when we prove things in math, we want to prove beyond like a shadow of a doubt, right? There's no way to falsify these sorts of things. So that's the next sort of thing that we have on here. They talk about evaluating an inductive argument. So an inductive argument doesn't prove its conclusion, but there are sort of different strengths that these arguments can have. So an argument is strong if it makes a compelling case for its conclusion. It's weak if its conclusion is not well supported by its premises. So going back up to this I would say is a pretty strong inductive argument. If you're failing every test you're taking, right? And you know a little bit about how classrooms are run, so that's probably gives you a little bit of ammo to say that this is also pretty strong argument. That's a pretty good argument is what I'd say. There's the other one, like I washed my car, it rained. I washed my car a second time, it rained again. I washed my car a third time, it rained again, right? You could do the car raining sort of scenario here. That would not be a very strong argument, right? We know that, like, things about rain, we know a lot of things. There's a lot of other factors at play there, right? So let's look at a few examples of some inductive arguments. You're nervous about your upcoming math class, but your friend who's taking the class with you assures you it'll be all right because you picked the top-rated professor on the professor rating website. There will be math tutors available in the learning lab, and you've set aside more time this semester to study. Explain why this argument is inductive and evaluate its strengths. So, what makes this sort of thing inductive? So you're nervous about your class, so what is he saying? Pick the top-rated professor, there's math tutors, and you've set aside more time, right? And so they're giving you specific instances, right? These are not sort of generalities, these are specific instances of things that you've done. And thus far, every time in your life, when you've picked a top-rated professor on your professor rating website, it has given you a good professor, right? So this is coming from like sort of experience, right? We've had these instances of things that happened. When we pick top-rated professors, they tend to be better professors. When we go and do math tutors, they tend to give us better grades. They tend to give us tutoring, which gives us better grades. And you set aside more time. So you've noticed a trend with the more time you spend on your studies, the better your grades are. The less time you spend on your study, the less good your grades are, right? And so you're making these arguments based on your previous experience, right? And so I would say one of the things that's kind of a giveaway that this is inductive is that you're making a generality based upon your experiences, right? So based on certain experiences or instances, right, you're generalizing like you should be doing better in this class. And we want to evaluate its strengths. I would say that's pretty strong. We know all those things will probably help you. There could be something that goes awry, but I would say that's pretty strong. The next one is the only two guarantees in life are death and taxes. So why is this sort of inductive? If we think about taxes, why do we have to pay taxes? Or what makes you think that you're going to have to continue to pay taxes? Well, so far in life, you've paid taxes. You've had experiences of paying taxes. Everyone before you has paid taxes. There's all these instances of people paying taxes that we can observe. And so in general, we think we're probably going to have to pay taxes till the end, right? Same thing with death. Why do we think we're going to die? Probably because everything that's ever lived before us is died, right? Everything that has a life has died, right? Pretty much. And we know people that have died, right? So there's this sort of thing. We see all these instances of it occurring around us, and we generalize that we are also going to be held to that standard, right? So the only two guarantees in life are so again, you're generalizing. And is this strong? Well, let's compare it maybe to like the class example, right? Death and taxes. So I would say death definitely would be like even stronger, right? So this is the sort of thing that happens with inductive arguments, and there's actually a historical example that I'll go into a little bit. But when we're talking about inductive arguments, we're trying to generalize off of specific events happening. And so we're really kind of limited to our own sort of perspective at that point. And so that's also another sort of reason why these things are not valid arguments, right? So going back to this one I think is pretty obvious. Like, you could go and do all these things, and maybe you just got a math teacher from hell or something, I don't know. You just end up like bombing the class, right? That is a possibility. Hopefully not, but it is a distinct possibility that could happen. Same thing here, right? We're assuming that we're going to die because everything we've seen thus far has died. But technically, and I wouldn't put your money on it, but you could be the first person to live forever, right? That's something that could happen. You could be the first person to not pay taxes, right? Well, no, you wouldn't be the first, I guess. There have been a few societies that, you know, before society even existed, wouldn't pay taxes. You know. But you could be the first person within the U.S. maybe to not pay taxes since the system was established. Okay. So again, these do not prove what we're talking about, right? This doesn't prove that we're going to die or have to pay taxes. This doesn't prove that we're going to do good in the class. Is it a good indicator? Yeah, it's a good indicator that it might happen. And so, a little bit of tangent. So in Western Europe, for the longest time, they saw, well, they looked around in their ponds and they saw swans. And what they saw were white swans, and they saw nothing but white swans. And so you could probably guess what they deduced from that. Inductively, they deduced that all swans were white. And so, lo and behold, they start exploring different places, and they explored Australia, and guess what they found? They found a black swan. And so sometimes you will hear this thing called black swan events, maybe. But that also goes to show that this doesn't prove it, right? So you're inductively sort of saying these things, but all it takes is one counterexample to prove you wrong, right? If you're saying the only two guarantees in life are death and taxes, all it takes is one counterexample of someone not paying taxes or someone not dying to show that that's not a true statement, right? And so these things are known as like black swan events. They're things that kind of change our perspective of things. So if you ever hear that term, that's kind of where it's coming from, right? Okay, so that is inductive arguments. Deductive arguments, on the other hand, we're going to apply two criteria to evaluating the deductive argument. So the first thing is whether it is valid. And this validity is sort of like, it is the setup of the argument itself. So we don't care if things are true or false. We don't even look at that. We just look at the construction of the argument and what the vocabulary is telling us in regards to like sets and members and those sorts of things. So the argument is valid if its conclusion follows necessary from its premise, regardless of the truth of the premises or conclusion. So we look first at validity. Is it set up correctly? Is the structure itself correct? So that's one thing we look at. And then the other thing we look at is if it's sound. So it's sound if it's valid and its premises are all true. So these are probably the arguments you probably prefer because they sound better in reality, right? We're not saying absurd stuff like we can with something that is just valid but not sound. So that is something that can happen. We can have a valid argument that is not sound. And now we're going to get to testing how things might be valid, right? So how are we going to test validity? So how we're going to test validity is by drawing a Venn diagram. So if we draw Venn diagrams that represent the information, and we can check to see whether the Venn diagram confirms the conclusion or not. So we want to evaluate the validity and soundness of the following arguments. We draw a Venn diagram. So the premise is all cows eat grass. And we had this before. So I think they introduced it as all cows eat grass. And I know I'm going to do some horrible English in this section. So just hopefully you know what I'm saying. So if it's a cow, then it eats grass, right? Is another way to say that. So these all blank do something, are blank is another way to state an if-then statement, right? So if you're a cow, then you're going to eat grass is another way to say all cows eat grass. And draw a picture talking about cows and I'm talking about things that eat grass on the outside. We know goats are not cows. So what is that telling us? This is giving us the existence of a member in a set. So if goats are not cows, what is that telling me about the X that I'm going to put here? So I want to put an X to represent the member of my set. So goats are not cows. So this is the cow bubble. I have to step outside the cow bubble. So I have some choices here. Here's my cow. I can come out here. Could I put a goat over here? This would mean a goat's not a cow, but it eats grass. This would mean a goat is not a cow, does not eat grass. So I could put an X here. I could put an X here. So what we're going to do is we're going to put it on the border. And what that means is it can go either way, right? And so their conclusion is that goats do not eat grass. Okay? Is that a valid conclusion? Can we conclude that goats do not eat grass? Well, that would be concluding that our X is outside of the grass circle. Can we conclude that? We cannot, because it's on the circle itself. So if it's on the circle itself, we cannot say that it's outside of it. So since we can't say it's outside of it, this is not a valid argument. And they asked if it's valid. If it's not valid, you can say right away it's definitely not going to be sound. Because for it to be sound, it has to be both valid and true. So right away, as soon as they say not valid, we can go right to not sound. Okay. I want to maybe take it back and show you what maybe a valid argument would look like, right? So this is a valid argument. So all men are mortal. So all men are mortal. And I know Socrates is a man. He exists in the set of men. So can I deduce that Socrates is mortal? Well, if I put him in the set of men, then he has to necessarily be in the set of things that are mortal, right? And so this is how you would prove the validity, demonstrate the validity of a deductive argument with a Venn diagram. And so it kind of forces one thing to be true, right? And so this, and I kind of said it, this actually proves things, right? This does not prove things. Okay. Good. One more page. Now we want to look at this thing. Evaluate the validity and soundness of the following argument. All of the crew of Apollo 11 were men. Buzz Aldrin is a man. Therefore, my conclusion is Buzz Aldrin is a part of the crew of Apollo 11. So let's draw this with the Venn diagram. All Apollo 11 crew were men. All Apollo 11 should be contained within the set that looks like men. Little wonky there. Everything should be that universe. Not the best drawn picture, but it gives a point across. So all of the Apollo 11 crew are men. Buzz Aldrin is a man. So this larger bubble is a set of men. I want to know, where do I put my X on this thing? I have to put it within this bubble. Do I put it, the other question is, do I put it within the Apollo 11 bubble? I don't know whether it goes inside or outside here, so I'm going to put it right on the border. And therefore, we're concluding Buzz Aldrin is part of the crew of Apollo 11. So, is that a valid argument? So based on what they're giving us, right, all the crew of Apollo 11 are men and Buzz Aldrin is a man, this is not a valid conclusion. We don't know whether this X is inside Apollo 11 or outside. So it's not valid. So if it's not valid, then it's not sound. And if this is a little confusing, it might be, right? Because all of the crew of Apollo 11 were men. That's a true statement. Buzz Aldrin is a man. That's a true statement. And even our conclusion, right? Buzz Aldrin is part of the crew of Apollo 11. That's also a true statement. But it does not logically follow from these two things that we stated, right? We only have these two sort of puzzle pieces to work with. We can't just go grabbing other information from anywhere and everywhere. So this is, everything in here is true, but it's not valid or sound reasoning, right? Another way you could like manipulate this, right? If you change the name Buzz Aldrin with anybody that's a man, if you put me in there, Professor Stevens, I guess, right? You can literally like put anybody's place in place of, but any man's name in place of Professor or Buzz Aldrin, and now I'm a member of Apollo 11. So I don't know what to tell you. It was hard, but I did it. Okay. So example 5. Oh, they give us a little bit of about structure. Okay, so this is what I'll say about this. If you told me these, I would have to think for a second for what this is. These are the basic sort of structures that your arguments can take. There are 2 of them that are valid. There are 2 of them that are invalid. I would not, like, students like sometimes look at this and they try to memorize this table, and I'm just like, why? Why the heck would you do that? Like, don't do that. Just draw your Venn diagram. If you draw your Venn diagram correctly, you understand how to construct the Venn diagram. It should get you through. I think it's a lot easier sort of approach to do, to be honest. I'm not a fan of rote memorization at all, right? And maybe I should go on a little bit of tangent on that, maybe. But everything within math, let's go back to that deductive logic, right? This is what we use to prove things in math, right? And so a little bit of a tangent. We use things deductively, but it's like you have to have premises to reach a conclusion, sort of thing. And so at some point, you can keep boiling down these premises, right? You can keep going from the conclusion down to your premises, kind of boiling these things down. And at some point, it's like the 2-year-old that keeps on asking why is the sky blue? Well, because of pigmentation and, color spectrum and how things reflect color and their chemical composition, and you can go on to all this stuff, and then they're still just going to ask you, but why? But why, right? And at some point, you just like start invoking like holy deities to explain things. It's like, I don't know, God made it happen that way, right? And at some point, you're just going to have to accept this for what it is. And so there is these things called self-evident truths, right? And there's these self-evident truths, these basic sort of building blocks that we want to base things off of. And in math, we call them axioms. So we have these sort of axioms that we build things off of. If you want some real examples, piano, this guy piano, they're really boring. Piano's axioms, Euclid's elements. An example of Euclid, the ancient Greek geometer, right? Trying to lay out the axioms of geometry. So that's what he tried to do around like 333 BC or something like that. Still use a lot of the stuff that guy did, right? He set forth a sort of structure that we still rely on. And so these things boil down to sort of self-evident axioms. You have an axiom. You have some sort of basic observation you make. Pianos, I believe, are about the integers. I could be wrong. It might be all real numbers. But his are about the number sets, right? And so we have two axioms. And we put these two axioms together. We do logical deduction to create math theorems. And that's basically all of math. That's all of math building theorems. That's basically all we do. We put two things together and we deduce them to create something new, right? And if the word self-evident like annoys you, what I want to say about that is good. It should, right? Like you should always sort of question these things, right? And a lot of math has come from questioning these things. Are the axioms really self-evident, or are we just assuming something that maybe we shouldn't, right? So there is that sort of component too. And there's that component of being enculturated, and so you don't realize you're assuming things that you shouldn't just assume. So these things come into play, right? All these biases and sorts of things. People think of like math as like this definitive sort of logical sort of thing, right? But there's a lot of stories within math. And people have a lot of sort of attitudes and opinions and emotions about these sorts of things. What was it, Pythagoras? Yeah, there was a the Pythagoreans were sort of a math-based sort of cult that existed. And Pythagoras was one of the people that came out of there. Although a lot of the stuff that is attributed to Pythagoras may not have actually come from Pythagoras himself, it may have just came from the cult. But it is like legend that like someone proposed the existence of irrational numbers. He went out on a little boat and never made it back. And so I don't know. There's a lot of math history that we don't know whether it really happened or whether it's like fabled or legend, you know, sort of thing. But yeah, it probably did happen. So it's kind of weird because you kind of expect that resistance with like, you know, social things and things of that nature, right? But it's just like with math, you think of it as being logic. Like who would be upset about that, you know? But people are. It happens. So let's get back to this in analyzing arguments. We're in example 5. Describe the form of the conditional argument and use a Venn diagram to test indeterminability. Okay. I don't want to spend a lot of time on the form, if I'm being honest. I would really rather you go with the Venn diagram. If you eat main course, then you may eat dessert. So we want to draw that. It's an if. It's an if-then statement. Oh, the first thing you put on there, that's not a surprise smiley face without eyes. That is a subset right there. So if you eat the main course, like a word that would represent you eat the main course, then you eat dessert. Desserts are super sweet. Deserts only have one S. Okay. You are not allowed to eat dessert. So you have to put that X outside your dessert. If you put the X outside of your dessert, does that mean that you did not eat your main course? Is this valid or not? So this is valid. So if this is valid, then it's either affirming the hypothesis or it's denying the conclusion. So I will give this one, this is denying the conclusion. Okay. Example 6. Describe the form, same thing, same instructions. If you want to dive underwater, then you must hold your breath. Again. Dive would be on the inside. Hold breath would be on the outside. The premise is you hold your breath. So we're in the hold breath circle. So now we ask, what about this circle? Is it inside or outside of this circle? We don't know. So we have to put our X on the border there. You want to dive underwater. Do we know that? Is this guaranteed from the picture we drew? Absolutely not. This is not valid. And this is not valid. If we go back, look at these forms, it is affirming the conclusion. Okay. And so we had 4 different forms. They're going to go to 4 different examples. Okay, so if you play drums, then you must keep timing for the rest of the band. You play drums, therefore you keep timing for the rest of the band. We have 2 circles. The others we're going to keep timing. So they say we play drums. So if we play drums, my X is going to go inside this middle circle right here that says drums. And if we play drums, is it guaranteed that we're going to keep the timing for the rest of the band? Absolutely. Socrates picture that we had earlier. And this is affirming the hypothesis. Okay, so now example 8, the last one. So hopefully we can draw this picture. If you build it, they will come. Okay, this is horrible pop reference, but there it is. Building James. I'm building it. And ball players coming, right? So you did not build the field. So if you did not build the field, that means our X cannot go in this circle. So our X has to go somewhere out here. So now we're looking at here. Does it go here? Does it go here? We don't know. So if we don't know, we have to put the X on the border. And they're going to conclude that no ball player will show up. Can we conclude that no ball players will show up? We absolutely cannot conclude that. So this is invalid. And if we look at the form, it's the only one that we have left that we haven't done yet. This is denying the hypothesis. So now we have this thing called a chain of conditionals. If P, then Q. If Q, then R. If P, then R. So let's look at this. So what P is a subset of Q. Is what that first thing. I have my P circle, I have my Q circle. And then the next one says if Q, then R. So that means that Q has to be a subset of R. Can we conclude if P, then R? We absolutely can. So this means that P is a subset of R, right? So if P is a subset of Q and Q is a subset of R, then P is a subset of R, is what this is saying. This is absolutely true. This would be also known as the transitive property, I believe. So if I'm friends with you and you're friends with Joe, then transitively I'm friends with Joe, right? Sometimes people say stuff like that. I don't know who says stuff like that. Sometimes people do. Okay, so we come back to this. Determine the validity of the following argument. I can't speak anymore. Determine the validity of the following argument. If you pay $59.98 to my MATLAB website, then you can have access to the online resources. If you have access to online resources, then you should have access to the e-text. Therefore, if you pay $59.98 to my MATLAB website, you will have access to the e-text. And so you might notice this is in the form of if P, right? And we have to make sure this is if P, then Q is what we're doing here. We're going if Q, then R, and our conclusion is P and R. So this is following that form that we saw on the previous page. This is so now they're going to give us something kind of similar. If you wash the dog, then I'll make dinner. If you mop the floor, then I'll make dinner. If you wash the dog, then I'll mop the floor. So maybe look through here. If we're doing our P, you wash the dog, make dinner is my key. Mop the floor. Oh, we're doing something new now. So this is R. Make dinner, that was Q again. Wash the dog was P. Mop the floor is R. So this is not the P, Q, Q, R sort of combo. We cannot conclude if P, then R. So this is going to be an invalid argument. Okay. And there's two last sort of things that we're going to do. So as I said, like inductive arguments do not prove things mathematically. They don't prove things, but sometimes they give you a pretty good handle at what's going on, and they will reveal certain patterns to you sometimes, right? And we can get a pretty good idea of whether something is actually a rule sometimes. So if we want to inductively test this, we got to come up with numbers for A, B, and C. So if A is 1, B is 2, C is 3, we can test it, right? 1 times 2 times 3 equals what? 3. 1 times 2 times 3. Sorry, same order. So you might want to do 2 times 3 over here, and then we're going to go 1 times 6 over here. So 6 is equal to 6. This is true, right? So this property works for these numbers. Does it work for every number? We don't know. We have not proven it. We have demonstrated for these numbers. If you want to try it, you probably want to try it. So if we do 2 times 3 And then multiply by 5. Is it the same thing as multiplying 3 by 5? 6 by 5, is it the same thing as 2 by 15 is 30 equal to 30? So we can check things. We can check things inductively in math, and it might give us a pretty good idea of what's going on. Just like in reality, right? The inductive things can give you a pretty good idea of going on, but like we really shouldn't rely too much upon inductive arguments, right? They are flawed and in their nature. They can be disproven, right? So deductive logic is something that is a bit stronger. It actually proves things. Is it true that this is a thing? A over B plus C over D equals A plus B over B over D. For all real numbers, A, B, C, and D, such that B and D are not equal to 0. Okay, so pick up some numbers. A equals what, 2, B equals, just pick some numbers, right? C equals what, 5, D equals, I don't know, 6. So now we're doing this. Is it true that 2 over 3 plus 5 over 6 is going to be equal to what, 2 plus 5 over 3 plus 6? So, try not to get too mathy in this class. Y'all try to avoid algebra, so I guess I'll get at it. But this isn't how you add fractions. So right away, if you do this, this isn't how we add fractions. If we add fractions, we actually want to add these things, we have to find common denominators. So in order to get a common denominator, I would have to multiply this thing by what, 2? This would be 4, 6 plus 5, 6 on this side. This side would be 7 ninths. So I believe this side is giving me 9, 6. I believe this side is giving me 7 ninths. And you might notice those are not the same fraction. So is it true that this is a property? So this is not a property. So if we did multiplication, right? A over B times C over D. So this is the one that looks like we just multiply straight across. So if we're doing multiplication of fractions, that would maybe be the property, right? But that is addition. When we do addition, and again, I had to do the work in here, right? We have to find common denominators. We can't just add straight across. And if you find common denominators, it's not the same as adding straight across. And we can do that, and we can dismiss this with an inductive argument, right? So we can disprove this with an inductive argument by plugging in numbers. So they do come in handy. Don't mistake me for knocking inductive arguments, but they are flawed, right? And it's important to notice or acknowledge the flaws that exist. And even this, I really should reduce this. This is 9, 6. I can divide both by 3 and what, 3 halves. 7 ninths is already reduced. Okay, so that is it for this section. I will be seeing y'all pretty soon. All right, take care.